Good evening, everyone. This is the sixth live discussion session, problem solving session of the course Soil Mechanics Geotechnical Engineering 1. In this session, I'm going to give some problems and solve them. The topic is shear strength 1. So, shear strength of soil, this chapter has been divided into two parts, the basics and some advanced problems in the next live session. So for this session, like the previous sessions, it has multiple choice questions, true false statements, and some numericals. So I'm going to start the discussion part later after I dictate all the questions. So I'll first of all dictate all the questions, and then I'll start. I'll give some time for those who have joined and who will join the meeting, and after that I will start discussing the solutions and giving the requisite explanations for the same. Okay, so right now I'm going to start dictating the questions. Those who have joined and those who will join later, please write down the questions or take a screenshot, whatever is feasible. And then after you write on all the questions, you get some time, 15 to 20 minutes to solve these questions. After which I'll again start the discussion session for the solutions part. Now, there is no need to leave the meeting. Please stay in the meeting and continue your work. So I'll start with the discussion. I start with the question dictation part. The topic is shear strength part 1. This is the sixth live discussion session, problem solving session of soil mechanics geotechnical engineering 1. So the first question is, in the Mohr-Coulomb failure theory, the critical shear stress causing failure depends upon. I hope you are familiar with the concepts of the Mohr-Coulomb failure theory. So in that theory, what are the factors on which the critical shear stress which causes the failure? It depends. Your options are properties of the material, normal stress on the failure plane, both of the above, or none of these. Sorry. I'll repeat the question. In the Mohr-Coulomb failure theory, the critical shear stress causing failure depends upon. Options are properties of the material, normal stress on the failure plane, both of the above, or none of these. Okay. Next question. The unconfined compression test is generally applicable for. The unconfined compression test is generally applicable for. The options are dense sands, saturated clays, weathered geomaterials, or none of these. I'll repeat the question. The unconfined compression test is generally applicable for, the options are dense sands, saturated clays, weathered geomaterials, or none of these. Okay. Next question. A cylindrical specimen of saturated clay 4 cm in diameter and 8.66 cm length is tested in an unconfined compression tester. Estimate the unconfined compressive strength and shear strength of clay. If the specimen fails at an axial load of 465 Newton and the change in length of the specimen on failure is 1 centimeter. I'll repeat the question. A cylindrical specimen of saturated clay 4 cm in diameter and 8.66 cm in length is tested in an unconfined compression tester. Estimate the unconfined compressive strength and shear strength of clay if the specimen fails at an axial load of 465 Newton and the change in length of specimen on failure is 1 centimeter. I hope the question was clear. I'll go to the next question. Yes. A cylindrical soil specimen fails under an axial vertical stress of 160 kilopascal when it is laterally unconfined. The failure plane makes an angle of 50° with the horizontal. Calculate the values of cohesion and angle of internal friction of the soil. I'll repeat the question once. A cylindrical soil specimen fails under an axial vertical stress of 160 kilopascal when it is laterally unconfined. The failure plane makes an angle of 50° with the horizontal. Calculate the values of cohesion and angle of internal friction of the soil. Okay. Next question. The angle between the direction of the failure plane and the direction of the major principal plane is, the options are 90 plus 5, 90 minus 5, 45 plus 5 by 2, or 45 minus 5 by 2. Phi is the angle of internal friction of the soil. I'll repeat the question. The angle between the direction of the failure plane and the direction of the major principal plane is, the options are 90 plus 5, 90 minus 5, 45 plus 5 by 2, 45 minus 5 by 2. Next question. The shear strength of a soil is a function of, your options are cohesion only, angle of internal friction only, both of the above, none of the above. I'll repeat the question. The shear strength of the soil is a function of, the options are cohesion only, angle of internal friction only, both of the above, none of the above. Okay. Next question. The shear test most suitable in the field is, the shear test most suitable in the field is, shear test is the test to determine the shear strength of a soil. The shear test most suitable in the field is, the options are direct shear test, vane shear test, triaxial shear test, or unconfined compression test. I'll repeat the question. That the shear test most suitable in the field is direct shear test, vane shear test, triaxial shear test, unconfined compression test. Next question. A sensitive clay has a shear strength of 45 kilonewton per meter square in natural state and 15 kilonewton per meter square in remolded state. The sensitivity of the soil is, the options are 30, 6, 1 by 3 or 3. A sensitive clay has a shear strength of 45 kilonewton per meter square in natural state and 15 kilonewton per meter square in remolded state. The sensitivity of the soil is, the options are 30, 6, 1 by 3 or 3. Okay. Next question. In a triaxial test, the relation between sigma 1, sigma 2 and sigma 3 is. Now what are sigma 1, sigma 2 and sigma 3? Sigma 1 is the major principal stress on the sample. Sigma 2 is the intermediate principal stress on the sample, and sigma 3 is the minor principal stress on the sample. So sigma 1, sigma 2 and sigma 3 major, intermediate and minor principal stresses on a soil sample. So in a triaxial state, what is the relation between this sigma 1, sigma 2 and sigma 3? Or what is the difference? What is the relationship between the major, intermediate and the minor principal stresses? So your options are sigma 1 equal to sigma 2 plus sigma 3, that is major equal to intermediate plus minor principal stress. Option 2, sigma 2 equal to sigma 1 minus sigma 3. This is the same thing actually. You can answer any one of them. That is, we get the intermediate principal stress by subtracting the minor from the major. So first and the second options are both the same. So I guess you will have an idea if they are correct or not. The third option is sigma 1 equal to sigma 2 equal to sigma 3. It is all the three stresses, that is the major, minor and the intermediate stresses. They are all equal. All the stresses are equal. And the last option is sigma 2 equal to sigma 3. That is, the intermediate principal stress is equal to the minor principal stress. Both are equal in magnitudes. Okay. I'll repeat the question. In a triaxial test, the relation between sigma 1, sigma 2 and sigma 3 is, sigma 1 is the major principal stress, sigma 2 is the intermediate principal stress and sigma 3 is the minor principal stress. So the relation is option 1 sigma 1 equal to sigma 2 plus sigma 3, option 2 sigma 2 equal to sigma 1 minus sigma 3. Option 3, sigma 1 equals to sigma 2 equals to sigma 3. Or option 4, sigma 2 equal to sigma 3. Okay. I hope it was clear. Next question. If the cohesion of a pure clay found in an unconfined compressive strength test is 1 kg per centimeter square, the unconfined compressive strength in kg per centimeter square is. So in this question, the cohesion is given in an unconfined compressive strength test. Now if the cohesion is given, then what is the unconfined compressive strength or UCS in kg per centimeter square? Your options are 0.5, 1, 2 or 4. I'll repeat the question. If the cohesion of a pure clay found in an unconfined compressive strength test is 1 kg per centimeter square, the unconfined compressive strength in kg per centimeter square is. Your options are 0.5, 1, 2 or 4. Next question. In an unconfined compression test, the soil fails under axial stress of 1.2 kg per centimeter square. The cohesion of the soil in kg per centimeter square is. So in this case, the opposite of the last question, that is the unconfined compression test is carried out and the axial stress is given. Now you have to find out the cohesion. The options are 0.5, 1.2, 0.6 or 0.4. In an unconfined compression test, the soil fails under an axial stress of 1.2 kg per centimeter square. The cohesion of the soil in kg per centimeter square is, the options are 0.5, 1.2, 0.6 or 0.4. Okay. Next question. Calculate the angle of internal friction of the soil in the previous question if the failure plane makes an angle of 65 degree with the horizontal. So in the previous question, this is the same data you have to use, and using this data, any or every data you can use, but you have to find out the internal angle of internal friction when the failure plane makes an angle of 65 degree with the horizontal. Okay, the options are 20, 10, 40 or 45. Calculate the angle of internal friction of the soil in the previous question if the failure plane makes an angle of 65 degree with the horizontal. The options are 20, 10, 40 or 45. Okay. Next question. In a strain controlled shear box test, the shearing strain is in a strain controlled shear box test, the shearing strain is. The options are decrease at a constant rate, increase at a constant rate, increase randomly, or kept constant. There is the direct shear test. Shear box test is the direct shear test. There are two kinds of tests. Test strain controlled or test controlled. I believe you are familiar with these two kinds of tests. So, in strain control test, what is the variation or how is the shear strain varied during the test? I repeat the question. In a strain controlled shear box test, the shearing strain is decrease at a constant rate, increase at a constant rate, increased randomly, or kept constant. Okay. Next question. In direct shear test, the plane of shear failure is. In direct shear test, the plane of shear failure is. The options are inclined at an angle of 45 plus pi by 2 to the major principal plane. Phi is the angle of internal friction. Option 2 can be inclined at any angle. Option 3 horizontal. Option 4 none of the above. In direct shear test, the plane of shear failure is inclined at an angle of 45 plus pi by 2 to the major principal plane, can be inclined at any angle, horizontal, or none of the above. These are the four options. Next question. Yes. True false statement. The Mohr envelope can be considered to be straight if the angle of internal friction is assumed to be constant. The statement true or false? I repeat the question. The Mohr envelope can be considered to be straight if the angle of internal friction is assumed to be constant. Is this statement true or false? Next question. Yes. In direct shear test, there is an effect of lateral restraint on the sample, the soil sample. Is this statement true or false? In direct shear test, there is a effect of lateral restraint on the soil sample. Is this statement true or false? Next question. The complex stress conditions across the soil sample in direct shear test leads to, the options are instantaneous mobilization of the entire soil strength. Option 2, progressive failure. Option 3, uncertainty in determination of strength parameters. Option 4, none of the above. I'll repeat the question once. The complex stress conditions across the soil sample in direct shear test leads to, the options are instantaneous mobilization of the entire soil strength. Option 2, progressive failure. Option 3, uncertainty in determination of strength parameters. Option 4, none of the above. Next question. A vein 10 centimeter long and 8 centimeter in diameter was pressed into soft clay at the bottom of a borehole. Torque was applied and was gradually increased to 450 kg centimeter when failure took place. Subsequently, the vein was rotated rapidly so as to completely remold the soil. The remolded soil was sheared at a torque of 180 kg centimeter. Calculate the cohesion of the clay in natural and remolded states and the sensitivity. This is a problem from the vein shear test. I'll repeat the question. A vein 10 centimeter long and 8 centimeter in diameter was pressed into soft clay at the bottom of a borehole. Torque was applied and was gradually increased to 450 kg centimeter when failure took place. Subsequently, the vein was rotated rapidly so as to completely remold the soil. The remolded soil was sheared at a torque of 180 kg centimeter. Calculate the cohesion of the clay in natural and remolded states and the sensitivity. Next question. The following results were obtained in a shear box test. So twice it was performed, once with normal stress 1 kg per centimeter square, for which the shear stress obtained was 1.3, and the second time the normal stress was 2 kg per centimeter square, for which the shear stress was 1.85 kg per centimeter square. So from this data, you have to find out the cohesion and the angle of internal friction. I'll repeat the question. The following results are obtained in the shear box test. When normal stress was 1 kg per centimeter square, the shear stress was 1.3 kg per centimeter square. When normal stress was 2 kg per centimeter square, the shear stress was 1.85 kg per centimeter square. From this data, you have to find out the cohesion and angle of internal friction. Okay. Next question. This is the last one. Again, data has been given from a triaxial test. The total axial stress of failure is 18 kg per centimeter square. Cohesion is 3 kg per centimeter square. The angle of shearing resistance or the angle of internal friction, the same thing, the 17.5 degree. Now calculate the lateral pressure. So the axial stress is given, find out the lateral pressure. I am repeating the question. The following results are obtained in a triaxial test. The data is total axial stress at failure is 18 kg per centimeter square. Cohesion is 30 kg per centimeter. The cohesion is 3 kg per centimeter square. Angle of shearing resistance, so the angle of internal friction is 17.5 degree. Using this data, you have to find out the lateral pressure. Okay. So 20 questions have been given. Okay. Those who have joined, please answer this question. I'll start the discussion part in another 15 minutes, 10-15 minutes. Okay. Hello, I hope I'm audible. Just share my screen. Okay, so I'll start with the discussion part right now. So the first question was, yes, the first question was, in the Mohr-Coulomb failure theory, the critical shear stress causing failure depends upon. The correct answer is, it depends upon both properties of the material and normal stress on the failure plane, because tau equals to, as we know, C plus sigma tan phi. So C and phi are the material properties and sigma is the normal stress on the failure plane. So the answer is both properties of material and normal stress, both of the above. Okay, this is the correct answer. The critical shear stress is defined as the shear strength. So the critical shear stress is nothing but this, the critical shear stress causing failure is nothing but the shear strength. This is shear strength. Okay. Next question. the unconfined compression test is generally applicable for? The answer is saturated clays. Why saturated clays? Because in the unconfined compression test, as we know, the equation for the minor principal stress is absent because it is unconfined. It is also called uniaxial. So there is only one equation, but there are two unknowns. We have to find out two unknowns from the shear strength test. One is the cohesion and another is the angle of internal friction. So when there are two unknowns, as there is only one equation, it will be very difficult to find out. It won't be possible actually to find out two of these parameters. Hence, to remove one, we assume that the value of phi is equal to 0. Phi is equal to 0, and phi is equal to 0 means the angle of internal friction equal to 0, and the angle of friction is 0 in which cases saturated clays have no or very negligible friction. Saturated clays have low or negligible friction. So in the case of saturated clays, the friction angle can be considered as 0, and if the friction angle is assumed to be 0, then the cohesion can be easily found out. So this unconfined compression test is generally suitable for saturated clays, because for other types of geomaterials or soils, the friction angle will come into play, and then it will be very difficult or impossible to find out two unknowns C and phi from one equation. Okay. Next question. A cylindrical specimen of saturated clay 4 cm in diameter and 8.66 cm length is tested in an unconfined compression tester. Estimate the unconfined compressive strength and shear strength of clay if the specimen fails at an axial load of 465 Newton and the change in length of specimen on failure is 1 cm. So over here, what we can do at first we can find out the initial area A0, initial area, it is pi by 4 d square. What is d? The diameter is 4. I think the value you will get approximately equivalent to 12.56 centimeter square. This is the approximate value. Now you have to find out the altered or the changed area to find out the UCS or unconfined compressive strength. So for that, the changed area A final, A0 and A final will be equal to how much? Will be equal to the initial area divided by 1 minus the axial strain. What is strain? Strain is change in length divided by the original length. This change in length, it is 1 centimeter. Original length is how much? 8.66, and A0 you have found out already. So the final area after failure or area at failure, using the same formula you can find out, you will get approximately equal to 14.21. Decimal places can vary as per your way of calculation, but you will get a value of around 14.19 to 14.21. Okay, this will be the value. Now once you have found out the area at failure, you can find out the UCS, compressive strength, that is QU. This is the UCS, equal to what? To be equal to the load divided by the area, that is 465, that is the load at failure, right? 65 Newton divided by the area at failure is 14.21. If you do this and you find out the UCS and convert it into kilopascal, the approximate result will be around 327.2 in kilopascal. Keep in mind, at first you'll get the answer in Newton per centimeter square. Okay, so in that you'll get the value of 32.72 in Newton per mm square. Sorry, cm square. Newton per cm square. Convert this into kilopascal, a standard unit. You'll get 327.2. Okay. Now this 327.2 is the unconfined compressive strength. What is the shear strength then? Now in this unconfined compression tester, I'll just draw a graph to just make you understand. If this is tau, shear stress, this is sigma, normal stress. Now the Mohr circle proceeds like this because sigma 3 is equal to 0. So it originates from the origin. So the diameter is the axial stress or the stress at failure. This diameter is QU. QU, this is the diameter or the unconfined compression test. The strength. This is the radius. Then that maximum shear stress is tau U, or it can also be said as Cu. Why Cu? Because we know that unconfined compression testing machine is used for testing saturated clays only, and for saturated clay the friction angle is absent. So in the equation we have tau equal to C plus sigma tan phi. So if phi equal to 0, then we get tau equals to C. That is, the shear strength is equivalent to or equal to the cohesion. It is equal to the cohesion. So tau U, ultimate shear stress, that is the shear strength, is equal to the cohesion. That is the maximum value of the shear stress. It is Cu. So we can see if Qu, that is the unconfined compressive strength, is the diameter of the circle, then Cu or tau U, that is the shear strength, is the radius of the circle. So it is basically half the UCS. So we can write that is the shear strength of clay, that is tau, shear strength tau U, like not like this. Tau U is equals to how much? It will be Qu by 2. It is half of the UCS, and the value in kilopascal will be 327.2 divided by 2. It is 163.6 kilopascal. Okay. So I can repeat. First of all, you need to find out the initial area, and then from the initial area and the axial strain, find out the area at failure. Then divide the axial load by the area at failure to find out the UCS. It is Qu. Half the UCS to find out the shear strength or undrained cohesion. You can also here call the shear strength as undrained cohesion, half of the UCS. Okay, because it is an unconfined compression test. I hope it is clear. I will go to the next question. A cylindrical soil specimen under an axial fails under an axial vertical stress of 160 kilopascal when it is laterally unconfined. The failure plane makes an angle of 50 degree with the horizontal. So here we can see sigma 1 is given, that is 160 kilopascal. Okay, unconfined, that means sigma 3 equal to 0. Sigma 3 equal to 0, and angle of failure plane. So here angle of failure plane alpha, if it is 50 degree, then we know, I think I've given in the next question. Before that, I'll just answer this question? Yes, this question I'll just answer first. The angle between the direction of the failure plane and the direction of the major principal plane. I should have given this question before. Anyway, so this is the plane of the major principal stress, that is sigma 1. Then if this is the failure plane, then this is the angle made by the failure plane alpha. And alpha has an equation, alpha equals to 45 degree plus phi by 2. 45 plus phi by 2, where phi is the friction angle. So in this question, third option is the correct one. Alpha equals to 45 plus phi by 2. Okay, now same equation over here. Alpha equals to 50 degree, that is equals to 45 degree plus phi by 2. Now upon rearranging, we'll get phi, that is the angle of internal friction, equals to, you will see, 50 minus 45 is 5, 5 into 2, 10. It is equal to 10 degree. Is equal to 10 degree. Okay. So the second part, angle of internal friction, we have found out 10 degree. Now the general equation for this test, that is sigma 1 equals to sigma 3 tan square alpha plus 2c tan alpha. 2c tan alpha. Okay. Now in this case, we have an angle of internal friction. If it was not given, we would have used the previous formula for saturated clay. Since we have angle of internal friction given, that means it is a C pi soil. For this, here we have sigma 3 equal to 0. So this equation becomes sigma 1 equal to 2c tan alpha. From here we can find out the value of cohesion. C equals to sigma 1 divided by 2 tan alpha. Now alpha is 50 degree. The value of C you will get around 67.12 kilopascal. Okay, sigma 1 by 2 tan alpha. So I'll just repeat, sigma 1 is given, the axial vertical stress, sigma 3 is 0, alpha equal to 50 degree equals to 45 plus phi by 2, find out the angle of internal friction, phi equals to 10 degree over here. The main equation is sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha. From here, rearranging the equation and putting sigma 3 equal to 0, we get C equals to sigma 1 divided by 2 tan alpha, the value of C we get as 7.12 kilopascal. Okay. Next question, I think I have told you, yes. The angle of failure, the failure plane makes an angle of alpha equal to 45 plus phi by 2 with the direction of the major principal plane. Okay. Next question. The shear strength of a soil is a function of, this is a very easy question, as we know, tau equals to C plus sigma tan phi. So the shear strength tau is a function of, it is a function of C, it is a function of phi, it is also a function of sigma. Okay, here I have asked function of cohesion only, angle of internal only, both of the above, none of the above, it will be both of the above, because C and phi are included in the function. So the shear strength is a function of both cohesion and angle of internal friction. Okay, these being the material properties of the soil material. Okay, next question. Yes, the shear test most suitable in the field is, it is vein shear test. Vein shear test. The others, direct shear test performed in the laboratory, also in the laboratory, and unconfined is a variation of triaxial test for saturated clays with no lateral pressure. Okay, the shear test most suitable in the field is the vein shear test. We have a numerical based on this vein shear test later. Next question. Yes, a sensitive clay has a shear strength of 45 kN per meter square in natural state and 15 kN per meter square in remolded state. Sensitivity of the soil is. Sensitivity is the degree of disturbance that was occurred in the soil. So in this case, sensitivity is defined as any property of the material that can be measured in the natural state divided by that same property in the remolded state. In this case, we have shear strength. Shear strength, we can write it as tau. Tau in the natural divided by tau in the remolded state. And since it is sensitive clay, tau can be also written as undrained cohesion, because for this the friction will be 0. So anyway, we write as tau natural by tau remolded. Shear strength natural over here is 45. Shear strength remolded over here is 15. So the sensitivity of this soil will be equal to 3. The fourth option is the correct one. Okay, I'll repeat once again. Sensitivity is the property, is a ratio of the properties of soil. The numerator is the natural property and the denominator is the property in remolded state. So in this case, we have shear strength, and for sensitive clay it is the undrained cohesion. So shear strength in natural state divided by shear strength in the remolded state will give us the sensitivity of the soil. Okay. Just a moment. Yes. I'll go to the next question now. Yes, in a triaxial test, the relation between sigma 1, sigma 2 and sigma 3 is. So sigma 1, sigma 2, sigma 3, as I've already mentioned, they are the major, intermediate and minor principal stresses respectively. So in this case, sigma 1, sigma 2 and sigma 3, the relationship, the last option is the correct option, sigma 2 equal to sigma 3, because when a soil is in triaxial testing machine, the confining pressure is same from all the sides, whether it is the x-axis or it is the z-axis. Only from the y-axis, the vertical, the axial stress is different. It is given in a different way. It is placed in the triaxial testing machine and it is surrounded by water on all sides, which gives equal amount of pressure from both the axes. Hence, the intermediate principal stress is equal to the minor principal stress, or we can say sigma 2 equal to sigma 3. We have only two stresses, that is sigma 1 the major and sigma 3 the minor. Sigma 3 becomes the minor and sigma 1 becomes the major. Okay, I hope it was clear. I'll go to the next question. Yes, if the cohesion of a pure clay in an unconfined compressive strength test is 1 kg per centimeter square, I've already drawn the diagram, but still I'll just again explain. So in the case of unconfined compression test in saturated clays, this is the diagram of the Mohs circle. Okay, this is the axial stress at failure, Cu, which is also equal to the UCS, unconfined compressive strength, and this is the maximum value of the shear stress, which is the shear strength of the material, tau u, or that can be also equal to Cu, because it is saturated clay, so the value of phi equal to 0. Phi equal to 0. So in this case, we have What do we have? We have cohesion given as 1. Cohesion given as 1. Okay. So you can see this QU is the diameter. So QU is the diameter equals to how much? It will be twice the radius, twice of CU. This is the cohesion. So what is the cohesion? The cohesion is found as 1 kg per centimeter square. So twice of 1 means it will be 2 kg per centimeter square. 2 kg per centimeter square. Okay. Same concept like the previous one. The unconfined compressive strength is twice the cohesion or the shear strength. Okay. Next question. Okay. Same testing. Axial stress. So here QU is given. This is the axial stress. 1.2 kg per cm square. The cm square. Now, what is the value of cohesion? Cohesion is the radius. It is half of the diameter. QU divided by 2 equal to 0.6 kg per cm square. So the third option is the right option. Here, okay, this is the last one. Yes, 0.6. Yes, it is 2. Yes. So we have axial stress at failure. It is nothing but the uniaxial compressive strength is QU given as 1.2. Cohesion is the radius of the Mohs circle, which is half of the diameter or half of the QU value, which will be half of 1.2, that is 0.6 kg per centimeter square. Okay. Next question. Calculate the angle of internal friction of the soil in the previous question if the failure plane makes an angle of 65 degree with the horizontal. Now, here, even though it is mentioned in the previous question, for calculating the angle of internal friction, only this is enough. Failure plane makes an angle of 65 degree. This is the alpha. Value of alpha equal to 65 degree, which is also equal to the formula 45 plus 5 by 2. Now, if you rearrange this equation and find the value of phi, it is 65 minus 45, it is 20 into 2 gives us 40, isn't it? The value is 40 degree. The value of angle of internal friction is 40 degree. And for this kind of questions, we only need the angle of failure plane to find out the angle of internal friction and vice versa. Okay. I hope it was clear. I'll go to the next question. In a strain controlled shear box test, the shearing strain is, obviously if it is strain controlled, strain has to do something with it, but whether it is increased or decreased, it is increased, because if the strain is increasing, then only we will have a graph in the positive direction, and if the strain is increased, the normal stress is same, the shear stress is increased, the shear force is increased based on whether the test is stress controlled or strain controlled. If it is strain controlled, in the dial gauge, we see the strain incrementing and then we record the values. If it is stress controlled, then the stress is increased and we record the value of stress from the load from the probing grain. So in this case, it is strain controlled. The shearing strain that is being applied to the soil mass in the box, it is increased at a constant rate. It is being increased at a constant rate. Okay. Next question. In direct shear test, the plane of shear failure is inclined at an angle of 45 plus pi by 2 to the major principal plane, can be inclined at any angle, horizontal or none of the above. Okay. So in this case, it is direct shear test. If it is triaxial, then this one, the first one will be the answer. But in the case of direct shear test, what do? We put a soil sample like this, apply here, shear force from here, normal load from here, such that the soil breaks from the center. One part moves to this side, another part moves to this side. So in this case, this is the failure plane. This is the failure plane, and this failure plane, in this case, it is predetermined that it will be horizontal. This is one of the limitation of the direct shear test, that in this case the failure plane or the plane of shear failure, it is being predetermined and it is essentially horizontal. Okay, so in direct shear test the failure plane is horizontal. Third one is the correct answer. Okay. Next question. Yes. The Mohr envelope can be considered to be straight if the angle of internal friction is assumed to be constant. So I'll just draw, this is tau, this is sigma. So in this case, if the Mohr envelope is straight, it is like this. It means what? It means the friction angle is constant, phi is constant. Okay. So the Mohr envelope, if it is a straight line, then the value of friction angle is constant. It is true. What will happen if it is otherwise? Suppose the Mohr envelope is not a straight line, it is curved line like this. It is a curved line. It means what? The angle of internal friction, it varies as per the tangent at each point. Here it will have a different value, here different value, here different value. Okay. So when the angle of internal friction is constant, then the Mohr envelope is essentially a straight line like this. And if it is not constant, if it varies, then at the point where tangent is drawn, we can join all the points and draw the Mohr envelope, which is generally not seen in homogeneous soils or C5 soils. Okay, but in C5 soil, in simplified condition, the Mohr envelope is straight line with constant angle of internal friction. Okay. Next question. In direct shear test, there is an effect of lateral resting of the soil sample. This is true because of the side walls. In this case, if it is a shear box, the soil is failing like this. Because the side wall, this is the side wall, there is a lateral restraint, and this is another limitation of the direct shear test. These side walls, they give an additional pressure, additional force to the soil, because of which there is a lateral restraint. So this is true. In this case, this is the sigma, this is tau. Okay. Next question. The complex stress conditions across the soil sample in direct shear test leads to. So in the case of direct shear, because it has so many limitations, first of all, horizontal failure plane which is predetermined, lateral distance from the sides, many complex stress conditions arise. Many complex stress conditions arise, because of which what happens is progressive failure. Progressive failure happens. That is, the soil mass doesn't fail at once, it fails gradually. And that means what? The mobilization of the entire soil strength, the shear strength which the soil has, if it gets mobilized, that means it is getting used up against the shear stress. So when it is getting mobilized, it is doing so by and by or gradually. Okay. The entire soil strength is not mobilized at one time. The mobilization of the shear strength of the soil, it happens gradually over a period of time, and this is an instance of progressive failure. So the complex stress condition across the soil sample in direct shear test, what does it lead to? It leads to progressive failure when The entire soil strength is not mobilized at once. It is mobilized gradually with the passage of time. Okay. I hope it was clear. I'll go to the next question. Yes. A vein 10 centimeter long and 8 centimeter in diameter was pressed into soft clay at the bottom of a borehole. Torque was applied and was gradually increased to 450 kg centimeter when failure took place. Subsequently, the vein was rotated rapidly so as to completely remold the soil. The remolded soil was sheared at a torque of 180 kg centimeter. Calculate the cohesion of the clay in natural and remolded states and the sensitivity. So this is the case of vein shear test, where the formula for torque is a torque. Okay, so torque is T. We'll give it as T. It is equal to pi d square. D is the diameter of the vein. D square tau f, that is the shear strength, into h by 2, this is the length of the vein, divided by 2, plus d by 6. D by 6. Now it has been said over here it is soft clay. The soil is soft clay, and we are asked to find out the cohesion of the clay in natural and remote states. For soft clay, we know we can write phi equal to 0 for soft clay. If phi equal to 0, then cohesion will be equals to the shear strength. Cohesion will be equal to the shear strength. In this case, tau f is the shear strength at failure. So the cohesion is equal to tau f, shear strength at failure. Okay. So what is the difference over here? The difference is we can rearrange this equation and find out tau f, it is equal to the cohesion. Okay. Now the difference is the value of torque is different. So we will use two different equations. The first one with T equal to 450 kg centimeter. Okay. So in this case, I will write like this: tau f, which is equal to Cu or C, cohesion, is equals to how much? It will be torque divided by pi d square into h by 2 plus d by 6. Now I will use this equation twice, once with T equal to 450, another time with T equal to 180. So for T equal to 450, we will get the natural case where it was not remolded. So for C natural, we'll get, once we put T equal to 450, D equal to how much? 8 centimeter, H equal to 10 centimeter, and again D equal to 8 centimeter. We'll get C natural equal to 0.35. There it is kg per centimeter square. Okay. And in a similar way, putting T equal to 180 kg centimeter, we'll get C remolded as 0.14 kg per centimeter square. Again, I am saying the decimals can vary as per the way of calculation. So this is the approximate answer: 0.335 for the natural cohesion or the cohesion in natural state, and 0.14 for the cohesion in the remolded state. Okay. So now the first two parts of the answer we have received, 0.35 and 0.14. And now the sensitivity, I have already mentioned in the previous question, sensitivity is the value in the natural state by the value in the remolded state, that is C natural divided by C remolded, and this will give a value of around 2.5. So I just repeat, torque equals to pi d square tau f, h by 2 plus d by 6. Tau f is the shear strength at failure. Now for soft clay, the shear strength will be equal to the cohesion because the angle of intersection equal to 0. Rearranging the equation, we get tau A for cohesion equals to torque divided by pi d square into h by 2 plus d by 6. Putting all the values for the natural and the remolded cases, we get the C natural as 0.35 and C remolded as 0.14 in kg per cm square. Now the sensitivity is equals to C natural by C remolded. The value of that is equal to 2.5. Okay. I hope it was clear. Next question. The following results were obtained in a shear box test. Normal stress 1 and 2, shear stress 1.3 and 1.85. So here it is very easy. We know the equation is tau equals to C plus sigma tan phi. Using this, we'll get the first one. Tau is equal to how much? 1.3 equal to C plus sigma is 1 tan phi, and in the second case it is 1.85, that is tau is 1.85 equals to C plus how much? It is 2 tan phi. This is equation 1, this is equation 2. Subtracting 1 from 2 minus 1, we get tan phi equals to 0.55. Okay, from which we'll get phi as approximately 28.81 degree, and putting tan phi equals to 0.55 in any equation 1 or 2, we get the value of C cohesion as 0.75 kg per centimeter square. 0.75 kg per centimeter square. Okay, so the main equation is tau equal to C plus sigma tan phi. We have two sets of values given. We frame two equations, we solve them to get the value of C and phi. Okay. Next question. Okay, here total axial stress is given. Calculate the lateral pressure. This is a classical case of triaxial shear test. Okay, I'll just write the data. At first, total axial stress at failure is sigma 1. Sigma 1 equals to, I just write 18. Okay, 18 kg per cm square. Then cohesion equals to 3 kg per cm square, and then phi equals to 17.5 degree. Calculate the lateral pressure, that is sigma 3. So what is the equation? Equation is sigma 1 equals to sigma 3 tan square alpha plus 2c tan alpha. And using this equation, you can use any other equation which is being reframed or modified from this. So from here, rearranging this equation, I will get the value of sigma 3. Okay, just a moment. It is sigma cube. Sigma 3 tan square alpha plus 2c tan alpha. Okay, now from here I'll get sigma 3 equals to how much? It will be ratio of sigma 1 minus 2c tan alpha divided by tan square alpha. What is alpha? Alpha equals to 45 plus 5 by 2, 45 plus 5 by 2. I think you'll get a value of approximately, yes, 53.75 degree. The value of alpha is 53.75 degree. You put all the values, sigma 1 equals to 18, C equals to 3, and alpha equals 53.75. Sigma 3, the value of the lateral pressure, you get as approximately 5.277 or 5.27. I'll write 5.27 just up to 2 decimal places. It can be 5.28 also. Just write 5.28 over here, kg per centimeter square. Okay. So I just repeat this question. In this case, in this question, we have been given a classical example numerical for the triaxial test, where we have the axial stress failure as 18 kg per cm square. It is the sigma 1 value, position C as 3 and phi as 17.5. We are asked to find out the lateral pressure, that is the sigma 3 or the major principal stress. So the formula is sigma 1 equal to sigma 3 tan square alpha plus 2c tan alpha. From here, if we rearrange the equation, we get sigma 3 equal to sigma 1 minus 2c tan alpha divided by tan square alpha. Now, to find the value of alpha, use the formula alpha equal to 45 plus pi by 2. Phi is the angle of friction, our internal friction, which is 17.5. We get alpha equal to 53.75. So 53.75 alpha we put in the equation and we get the value of sigma 3, that is the lateral pressure, as approximately 5.28 kg per centimeter square. 5.28 kg per centimeter square. Okay. I hope the solutions are clear. So thank you those who have joined in the class. Next class will be on the coming Monday, that is 9th of September, with the second part of the shear strength, and that will have only numericals. Okay. Thank you so much.